Okay, Brenda, let's start. Ladies and gentlemen, welcome to the webinar of Structural Optimization on Modern Bridges, which is supported by YAPSET Technology Commission 2, Task 2.4, Structural Optimization. I'm Xiaoyu Luo, Associate Professor from Chang'an University. And this webinar will be recorded. If any one of you have any question, please put the Quest or A buttons, and then Brenda will open your mic and you could ask the question. Firstly, let me introduce YAPSEP for you first. YAPSEP is International Association for Bridge and Structural Engineering. And YAPSEP's mission is to exchange knowledge and advance practice of structural engineering worldwide, and all aspects in structural engineering, all types of structures and structural materials, and all aspects of construction process. And now we have members from more than 100 countries. And we have the YAPSEP founded in 1929 and from Zurich, Switzerland. Now the president of YAPSEP is Tina in Denmark. And our goal is to do with all aspects of structural engineering, scientists, arts, planning, design, construction, operation, monitoring, and inspection, and so on. And we have the following objects to promote cooperation and understanding among all these concerns with structural engineering and related fields by worldwide exchange knowledge and experience. The second is to encourage analysis and responsibility of structural engineering towards science needed. Third is to encourage action necessary for progress in structural engineering. Four is to improve and foster cooperation between organizations having similar objectives. And for the purpose, the association, including organize conference worldwide and publish the high-quality journal, Science Engineering International, Structural Engineering International, and then we call SEI, and publish book reflect the words of its technological groups, and create technological groups as required by new needs and technology process, offer the possibility to join activity within national groups of YAPSET, offer a progress for young engineers, and present annual awards. And the highest body of our association determine the long-term object of the associate, encourage it, promote it, and control its activity, and ensure that necessary means and available. And this is the exclusive committees, and formally the stand orders govern the action of WIRE groups, establish link with other organizations, and set up non-technical groups, assess the activity of TC and appoint its WIRE chair and members, define the terms of see that Brenda. Okay, thank you. And I'll share the slip quick. And we have several boards and commission, and we will make the awards every year. And then we have a journal. And then we have every year we have the meetings. This is coming from this year, September, and next year in Tokyo, and then in England. And okay, we have the activity of commission. Indeed, we have 6 now. Tonight or to date, we have the commission 2, conceptual designs. And you could find the deliverables and all the successful events before from our website. And under Commission 2, we have TG2.4 structural optimization, which we hold this webinar tonight. And thank you, and thank you for attendance. And we also welcome every one of you to join the YASEPs. And so let's continue tonight's webinars. Two topics will cover in this webinars. The first one is address to structural engineering motivation to design and build new ultra-high performance fibers reinforcement simultaneous composite bridge, that which we call UHP FRC bridge, as cost-effective lightweight structures of original aesthetic expression. Besides stance, basic principle, conceptual design, as well as design optimization and construction will be discussed. The second is focus on the structural optimization for pylons of cable-supported bridges, including the programming methods of biological evolution structural optimization and the application in engineering fields. The first one will be given by Professor Eugene, a good friend of me. So let me introduce him for you first. From 1995 to 2023, Eugene Bewelder was professor for engineer of existing structure at EPFL, that is Swiss Federal Institute of Technology in Lausanne. Among these topics, his teach and research activity including the use of UHP FRC Well, I'm sorry for my lost. Eugene, please.
Yes, thank you. Thank you very much, and welcome everybody to my lecture, Design Optimization and Construction of UHP FRC Bridges. In the next 40 minutes, I will very quickly go through 4 chapters. The first 2 are about conceptual design and some basic background regarding resistance models. Then we will look at the case study in order to apply all these principles. And finally, the last part is showing you some built UHBFRC bridges. Now, what is UHBFRC? UHBFRC stands for ultra high performance, fiber reinforced, cementitious, composite material. You see here on the screen a cross section through this material. The white spots are steel fibers, a huge amount, and the dark parts are the cementitious matrix. This is a very compact matrix consisting of powders and particles, cement, etc. It is impermeable and thus watertight to water, even if you apply a tensile stress under service conditions. So this means this watertightness is actually the guarantee why this material is very durable. The fiber reinforcement, the steel fibers, there are at least 3% in volume of very thin steel fibers with a slenderness of 65 at least in this material in order to obtain strain hardening in tension. Strain hardening is the behavior beyond the elastic limit, and the elastic limit for good materials is at least 10 megapascal. And then after the strain hardening behavior, we will get the tensile strength at about 14, 15 megapascal. The compressive strength of this material is around 150 MPa, and the modulus of elasticity is usually between 45 and 50 GPa. We have standards worldwide, in particular a standard in Switzerland that I use often. Now, why should we build using UHBFRC? The objective is to obtain UHBFRC structures that have a better performance in terms of cost, durability, and environmental impact compared to traditional construction. Traditional construction, I mean reinforced concrete and steel construction in particular. Actually, we take the best of both of these traditional construction methods in order to obtain a new construction method, which also allows for original aesthetics. We will get lightweight and durable structures with lowest possible environmental impact. And hopefully this lecture might change your mindset a little bit at least. And I will begin with 5 design principles. First of all, principle number 1, UHBFRC is not the concrete, is also not the steel. It is a composite material. It's very important to think in terms of a new type of material. The design approach for massive structures like the ones in reinforced concrete does not apply to lightweight structures in UHBFRC. I see several applications using such materials which are quite massive, where you can see the influence of reinforced concrete. Of course, this is not the objective, to replace traditional concrete by this high-performance material. That would lead to ineffective structures, too expensive, too costly structures. Okay? Such materials are under the name of UHPC, which is in many cases just a better fiber-reinforced concrete. They have moderate fiber contents, smaller than 2% in volume, typically, and as a consequence, rather moderate mechanical properties. And these materials are, as I mentioned already, designed like reinforced concrete. This is not the way to go here. So what I'm introducing here today is UHBFRC and the very specific design principles that belong to this material. Principle number 2 is, of course, we have to explore the material properties of this new material. In particular, the tensile properties, the elastic phase, the strain hardening phase, and also the significant softening phase of the tensile behavior here, the whole domain. We have a quite significant deformation behavior, or in other words, ductility. This resembles to steel somehow, but of course the stress values are much lower. And that's why it is very interesting to combine UHBFRC with rebars. And from a mechanical viewpoint, this is rather simple. We add the response of steel rebars with the response of UHBFRC. It's a simple summation, the structural behavior. And since steel rebar costs the same price per kilogram like a kilogram of UHBFRC, it is, of course, very interesting to add steel rebars, but only in the main direction. We do not reinforce like in reinforced concrete. It's different. Only in the main direction. Also, post-tensioning is, of course, reinforcement that is very interesting in the world of UHBFRC structures. So we exploit the tensile strain hardening. There are no cracks. We don't need to design for cracks or stuff like this. There is no water ingress under service conditions. Durability is very simple to be designed. Since we are working with lightweight structures, the serviceability limit state is very important. And the significant performance of our UHPFRC is actually the very high stiffness under service stresses here. Since we have no loss in stiffness by cracking, which is very well known from reinforced concrete, we have a crack-free situation. The elements have a high stiffness. Principle number 3 is to design structures in our UHPFRC, how to exploit the best from traditional reinforced post-tension concrete and traditional steel construction. As already mentioned, we use only the best materials, cement, other reactive powders, superplasticizers, of course. Steel is a high-performance materials in terms of fibers, rebars, pre-stressing, and we fully avoid gravel, too much water in concrete. These are the sources of durability problems in concrete. And we are seeking and designing for lightweight structures, a high ratio of traffic load to self-weight. We produce precast elements and assemble them by methods of rapid construction that we take from steel construction. We cast, glue, post-tension in order to assemble elements. We do not lose time and introduce problems with welding in order to realize joints. Principle number 4, optimization of design. The objectives are, we like UHPFRC, but we use UHPFRC with the best possible mechanical properties, and we use the least amount of UHPFRC. So we go for the best, but use as little as possible. That's optimization. And the higher material cost because of high fiber content is clearly and largely outbalanced by less material volume necessary. The lightweight elements will simplify the construction process, accelerate construction, which is also a reason why the cost can be kept down. And principle 4B, again, optimization is actually the creation of an equilibrium of aesthetics or cultural values and economy. You see here some points what I mean under economy and aesthetic creation. Of course, slenderness, boldness, elegance. And actually for the design, the most important thing is to find the best stiffness or rigidity of the structural elements. Now, principle number 5 is finding inspiration. And construction history is an extremely rich source of inspiration. For example, we have here François Hennebique, the first time of reinforced concrete at the end of the 19th century is a rich source of what we can do today with UHPFRC. Hennebique would have used UHPFRC at that time if he had the chance to have this material available. He was already thinking in terms of a combination of steel rebars, and cement, not concrete. Another source of inspiration is, of course, cast iron, also from the 19th century. And even aluminum structures can be interesting as a source of inspiration. But also modern structures like this pedestrian bridge would be, I think, even more interesting if we could replace this nevertheless rather massive post-tension concrete deck here by a lightweight UHPFRC deck. So study existing structures made in traditional materials and deduce improvements thanks to UHPFRC. Okay, I would like to summarize this introduction We seek for lightweight structures, precasting, accelerated construction. We have for free practically durability, and to control the design, construction cost must be lower than the cost for traditional designs. If you don't achieve this, then your design is not good. In terms of weight, it should be at least 3 times lighter than what you know in case you are a designer in reinforced concrete. Here are some sketches of the conceptual design principles for flat slabs. So the maximum thickness of flat slabs is 150 millimeters. By the way, we express everything in millimeters, not in centimeters. It's like in steel construction. I would say 150 millimeters is already very thick. The thickness is such that actually we can put hollow cores into such a cross-section, pipes for services, and so on. So we are mostly looking at thin slabs and ribs. Ribs of varying heights, integrating rebars. This is the design approach that we have. Or when it comes to plate girders, we have here precast elements in bright green, and then on site we cast UHPFRC in place, fill all the joints in the longitudinal direction and also in the transverse direction, such as to obtain a monolithic structure. These are U-shaped cross sections, trough elements with slab at the lowest level, here at the higher level, always with the cross girders, transverse ribs, longitudinal ribs. Of course, this design with ribs has been inspired by steel construction. Here we look at the box girder, again with ribs in both directions. The slab up here is only 60 to 80 millimeters thick, or thin, rather more. Of course, we use post-tensioning, which is in the most case, of course, external post-tensioning, because we want to keep the web as thin as possible, up to 150 millimeters only. So this would be for box girder. And very interesting, UHPFRC has a big potential in order to be used as a partner for steel or timber in order to create composite girders, lightweight composite girders. Such a slab is 3 times lighter than slabs in reinforced concrete. This has a beneficial effect also on the steel structure here or the timber structure down there. For those who are still nostalgic with reinforced concrete, this is a concept how we should design reinforced concrete nowadays. We can still use reinforced and post-tension concrete girders, maybe precast or cast in place, but then the exposed surfaces need to be strengthened here in green with UHPFRC. So let's have a quick look at the resistance models and how we can verify structural dimensions. Of course, we need to fulfill the common design principles that apply for all construction methods, service conditions, then of course ultimate limit state, where we assume yielding of steel rebars and UHPFRC tensile strength, and on the other side compressive strength. Serviceability limit state already, it has to do with deflections, and of course the dynamic behavior is very important since we are working with lightweight structures, but I can already mention from experience with pedestrian bridges the structures are just sufficiently stiff that we do not fall into the dangerous frequency domain in terms of vibrations. Fatigue is, of course, a limit state that we need to check, in particular for railway bridges. The basic format to verify, I think you know all this. We need to find out about the coefficient about the resistance coefficient. We apply in Switzerland, of course, the European concept for dimensioning. And we usually apply a coefficient which is 1.3 for plain UHPFRC. The sectional model for ultimate limit state under bending is shown here. We assume that strains remain plane or cross sections remain plane under bending. We have a linear distribution of strains. We can then calculate the stresses in the cross section on the compressive side above the neutral axis here. We have usually linear distribution of the compressive stress in UHPFRC. And on the tensile side, of course, we have the contribution of the rebar plus the contribution of the UHPFRC with its tensile strength. Internal forces equilibrium allows us to determine the ultimate moment. Interesting is, of course, shear, as usual. And what's new is actually that UHPFRC takes tension, tensile stresses, not only compressive stresses, which enhances the shear resistance to such a point that actually shear is no longer really a big issue in the design process. So we see some similarity with the steel construction, where we usually don't have a concern with shear design. Here you see more in detail what the very simple equation is in order to obtain the contribution to shear resistance, the contribution by UHPFRC. The index U is always referring to UHPFRC. Then, of course, adding the contribution of vertical rebars that can be single rebars, not just, we don't need to put stirrups. Single rebars, well anchored, of course, up and down, they are very effective in case of high webs or even integrating post-tensioning cables or pre-stress. Then fatigue limit state, we need to conduct an analysis of the quasi-elastic sectional stresses. We have in the bottom part of the tensile side the contribution of the steel rebar, the stress, the fatigue stress in the steel rebar, and also the stress in the UHPFRC. Now, this stress usually is in the hardening domain, beyond the elastic limit. So that means we need to find this stress distribution by iteration. Once again, when we look at the moment curvature diagram, the elements in our UHPFRC do not lose their stiffness, or let's say only slightly. They behave like steel. This is a significant performance compared to reinforced concrete, where after a very short initial state 1 behavior, we have crack formation and the cross sections become quite lose their stiffness in order to find themselves in state 2. So this is a very important difference. Yes, once again, this is for the fatigue design. I will come back to that now. This is the third part, the case study of a short span. It's only 6 meter span railway bridge that we built already 6.5 years ago. And I had the chance to follow this design from the initial idea until the quality control at the very end of execution. So it's not an impressive structure, but it offers all the difficulties and all the challenges that you can have in design bridges, in particular railway bridges, and in particular the design of cross-section with respect to fatigue, because fatigue was actually the initial, or was the decisive design determinant criteria. So you see on this picture, actually, it is a replacement project of a damaged reinforced concrete structure, and we had a very reduced and limited construction height here. So when we look at cost, by the way, it is not just the cost for the material and the production of the UHBFRC element, it is also the adaptation, for example, of the railway track, which was not necessary thanks to the use of the new material. And that's a significant cost issue. So what did we build? We did we designed a ribbed slab here, a thin slab of 50 millimeters, and then ribs containing 2 rebars. That's the slab element, and we have side girders that need to take, or that we designed for taking impact loads of the road vehicles. As I mentioned, fatigue limit state and serviceability limit state was determined. You have here an overview of this rib slab and the edge girder with a massive part and the top part, which looks like a structure from steel construction. So the stiffness of the structure was actually really the most important issue here. Again, we applied this already introduced model in order to obtain the bending resistance. Same for the shear resistance. These are hand calculations that I am able to do. And then, of course, the design is always controlled using finite element analysis. But with the hand calculations, you get about 10% right already. Now, with respect to the fatigue, very important. So we have the lower part of this rib in tension, where we have the 2 rebars in this case, rather thick rebars. They are in tension, of course, and also the UHBFRC material. It is, however, in the strain hardening domain, and thus it loses its stiffness a little bit, this lower part, and we have to find the strain, and in particular the stress distribution of this type in the cross-section by iteration. But this can be done even by hand calculation, or of course with the corresponding cross-sectional numerical model. So we verify in terms of on global level, in terms of the structural element, which is a very simple verification. We need to keep the stress lower than 50% of the ultimate resistance. This is what this equation says. And then we check on the material level also locally, in particular that the rebars contain a fatigue stress that is lower than the fatigue endurance limit. That's all. Very, very short and clear fatigue design, but very important in this case. We had the chance to do suitability tests on on a high girder with 2 ribs. Here we have the bending case. So this simulates a equally distributed load on the beam. These are the recorded force deflection curves, some digital image analysis in order to be able to see, recognize, identify some hairline cracks that you would not see by your eyes. So we have to go up to 73% of the ultimate resistance in order to see some hairline, I call them matrix discontinuities. And then, of course, eventually we have the fracture. These tests allowed us to determine the beam stiffness, which is an important property for elastic behavior. Similar, the shear test with a single eccentric point load at a nice shear span where we can expect a shear failure. Let's look at the DICs. And we have a formation at 82% of maximum force of, let's say, a trend in order to create 3, what is usually called critical shear cracks. And finally, the fracture occurred here. But we had significant bending, micro crack behavior also at ultimate limit state. Now, of course, we would like to analyze or back calculate such tests. And these are the values, the models that my co-workers, younger co-workers assumed in order to calculate the tests before the tests were conducted. And here is the comparison. So they calculated the red line without knowing the black line, which is the experimental one. And we can notice that the prediction was very precise in terms of ultimate load, and the stiffness was only slightly overestimated. So we have very reliable structural models in order to analyze such beams. Okay, let me go on. Of course, we can also deduce from such structural analysis the cross-sectional stress distribution in order to understand how the behavior is. We can simulate, of course, what is called cracking of the beam or cracked zone and compare with reality. Let me go to, yes, just some picture from the construction. So all 4 elements were cast in one morning, one day, so very fast. And of course, we didn't have much time in order to build all this during a night shift in November 2017. Everything went smoothly. This is very traditional, as if it were an element made of a traditional material. Just a remark, the UHPFRC material cost in this project was less than 10% of the total construction cost. Once again, look at this structure after the construction and already in service. We did some, or still do, some monitoring of this structure, and the allowable deflection of 3 millimeter is by far not reached. This has to do with the over-conservative load model according to European standards. Over-conservative which means in this case of a short span bridge, which is about three times over conservative with respect to reality. But that's another problem we can discuss at some other meeting. Okay, we measure a lot of things here. Of course, it's an application with experimental character still, but nevertheless, it confirms our design assumptions and our expectations. This is a view of another short span bridge built in 3 years ago. And currently, we are working on the next project that will be realized this autumn. And there are other projects on the way. This is a design of a large structure for those who need to have large structures in order to be convinced. This is the design alternative in post-tension R UHBFRC. The cross-section looks like more like a steel structure. And down here, we have a traditional post-tension reinforced concrete. So we can compare directly the two designs. We use up here for the innovative design, we use 4.5 times less building material. We have a 55% lower environmental impact, 22% lower construction cost, 50% shorter construction time. We have all the arguments here. Nevertheless, conservative civil engineering will still do the old-fashioned design. Some exemplary applications here, pedestrian bridges, of course. This is a pedestrian bridge we built 9 years ago. We are observing it, and we had the fun to design this structure, which has an asymmetric cross-section here. It is a short span structure only, and we incline here this web by 15 degrees. And you see here the dimensions in millimeters, 40 millimeters, 50, it's the slab here, and so on. It's lightweight, it's slender. The rebar configuration, only main rebars. There are no constructive rebars like we know them from reinforced concrete. Let's look at the construction. This is the matrix in order to produce the what we call the organic web of this pedestrian bridge. Installation, the whole bridge, the girder was installed in one morning in an urban area without having lots of place for the construction site. Things are post-tensioned and put together. Here, some post-tensioning, and it's a very effective and fast and rapid construction method. Some impressions from this pedestrian bridge, which has also a, let's say, an experimental character, but works very well in practice. Here, really, we tried out what is possible with this material. Look at this very fine arrangement of details. All of them perfectly well realized. Another pedestrian bridge, also with a U-shaped cross-section from the design sketch to the construction plan, 26-meter span, no particularities to realize in such structures. It became like a routine construction. Another view, and this is a particular pedestrian bridge over railway line. Everything is in UHBFRC, post-tension UHBFRC. Everything is monolithic. There are no no bearings and other things that need maintenance. It's all fixed, monolithic, put together. It's all precast and mounted in one night over the railway line in an urban area with no access to the construction site. Things were lifted in by a big crane, with the advantage that the elements were, of course, relatively lightweight. Some other views, we are in the town of Montreux. Some of you might know it because of jazz festival. This is a road bridge, 26-meter span. Again, we had to relimit the girder height to the least minimum. We have 1.25 at midspan and only 0.75 here, because otherwise the construction cost for adapting the road on both sides or to go deeper with the river, those costs would have exploded. So we have just the perfect solution here in order to accommodate for all these severe requirements. And here we fully applied this basic principle that I introduced before at the beginning. So precast girders and then cast in place UHBFRC in order to form a monolithic structure. Even we cast in place UHBFRC, we go beyond this very critical joint detail. There is no dilation joint. We go onto the road, and we have some joint detail here on the roadside. So this is quite original as a detail. Some impressions from the construction site, precasting of the girders, placing them, casting the UHBFRC. Actually, this process took 5 working days. So that's rapid construction. And the cost was very low compared to other designs. It was by far the design with the least cost compared to traditional designs. Here a composite girder, timber, and a thin RUHBFRC slab. Of course, this is very interesting in terms of CO2 emissions. Very easy to be built. In particular, it's the appropriate material, timber, of course, in an area where we are actually in the middle of a forest. And I would like to show you a last slide, which I took the day before yesterday on a railway viaduct, on a large railway viaduct in Switzerland. And we have here actually a riveted steel structure from 1896, which gets new RUHBFRC trough elements in order to take the ballasted track for modern traffic use. In the future, there will be a composite action by welding here and here. And actually, this helps here to rescue a viaduct from 1896 in order to make it, to give these necessary performance in order to accommodate for new traffic needs for the next 100 or probably 1,000 years. I thank you for your attention.
Oh, thank you, Eugene, Professor Eugene. And I think this slab's just so excellent. This lecture. And the light and beautiful UHBC bridge, like the timber UHBC, UHBFRC, I never see before, impressed me most, as well as the design and optimization idea and methods, and that's also very good. I think UHBFRC can be regarded as the first revolution in the world of civil engineering. I think this material will be widely used in the future and will emphatically improve the performance of bridges. So, ladies and gentlemen, if you have any questions, you can raise your hands and use the mic to ask. Thank you. Is there any question? Yes, you can type your question.
There
If
is
any, if
no
any.
question for the time being in the chat, but we can. I suggest, Xiaoyu, that you continue and maybe we do everything in the end, the Q&A.
Okay. Okay.
Okay.
Maybe the audience could not use the mic. So now, thank you again for your times and
My pleasure.
experience. Okay, and the question maybe later we could write in the Q&A. Now I'll try to share my screen and start the second part of my lectures. Okay, and does everybody see my screen? Maybe the internet is not so good in here.
We can see you. Can just go on the presentation.
Okay,
okay.
That's good.
Oops,
I'm
now
sorry.
we lost the presentation.
Now I will try to share this again. Sorry about this.
It's coming back.
Okay, thank you. And my topic is about the optimization for the pylons of cable-supported bridge from vessel algorithm to engineering application. When we're talking about the structural optimization, maybe we could look back to 19th century. The sandbed cable arch model was used to find the reasonable hyperbole of the Sanguara Familia's vault. And this test just finished by Antonio Gaudí. And all of this sandbeds was used to find the shape. And yes, the sandbed was attracted by the earth, by the gravity. So when we put upside down the all of the model, and this shape of the model should be the best shape to resist the gravity. And that's the very beginning of the structural optimization. And until 1930s, and indeed a very famous designer called Robert Mallar, he also used another method to finish the conceptual design of such an notable bridge. And he supposed in these 2 points they have the force concentrations, and with these 2 force concentrations, and the negative bending moment is just like this, and this is the same because this is a 3-hinge arch. We know that, and this one is the bending moment caused by the horizontal flux. It's going like this. So when we try to put these 2 bending moments diagram together, and we will find this is the last part of this. And you know, this is just the same shades with this structure. So design or make optimization according to the bending moment, is a very useful thing for the structure to have a better performance. In this case, the Robert Malar also enlarge the shape of the piers. Let's look back to the cantilever elements. When the wings have attacking to the piers, I'm sorry for this, I'm not so sure. And the bending moment will be going like this, and just the same shade of the piers. That's very interesting. That's mean in R-based mountains, even the strong winds coming, this bridge will be safe and have a better performance. So, and let's look a little bit earlier, the upon the material piers by Gustav Eiffel. And you could find out that Eiffel just used the same shape of the two-hinge arch, the bending moment of two-hinge arch, the same shape. That's very interesting. And to 1992, the Alamillo Bridge by Calatrava, they also shaped the pylons according to the bending moments of the live loads. And Suniper Bridge in 1997 by Christ Mayans, he also shaped the pylons here. Here's the connecting point or the curved trench points according to the bending moments. You know what? The bending moments here just 0. So this is a very amazing method for structural optimization. But now in 21st century, we use the computer for the to add the design. So we do the structural analysis, drawings, and could we do the structural optimization by computer? I think the answer is yes. So this is our contents about the structural optimization by computer. Firstly, I try to talk something about the concept and stage of structural optimization. Then I will try to explain the theories of bidirectional evolutionary structural optimization, which we call Basel. Then we will try to do the Basel algorithms. Then we will use we will talk something about the engineering application. Firstly, when we're talking about the structural optimization, indeed, we have 3 levels for the structural optimization. This is the very basics, is the topological optimization. And then the second level is the shape optimization, and the third level is size optimization, which is just corresponding to the conceptual design stage and preliminary design stage and detailed design stage. Let's start from the detailed design stage. And if we have the condition about the, this is a charge with a force going to the right. And actually, when we put the size optimization to this situation, and definitely the force will go directly to the connecting point like this. So this element just not so important as this one for this force. So the answer would be like this. This element will becoming strong, and this element will become less strong, and the dimension will be the dimension optimization will be finished. But actually, in the size optimization, we cannot change the critical points of this. We could not change this. We just change the shape of the elements. Second is the shape optimization. Such like this case, we have a hole inside the plate and we give a load to the right. Actually, the load have to be transferred to the foundation directly, of course, directly, but there is a hole. and the force have to go like this. That's not directly. And after the shape optimization, definitely the hole will become more slender, let the force could go more smoothly to the foundation. But actually the hole will not disappear under this level of optimization, because we just could change the shape of this hole, but we could not eliminate, or we could not fill the hole. So about the topological optimization, I think that is the most flexible method for us to make a optimization, especially for the conceptual design, because under this situation, we can change and remove or adding some material freely. So that means we could have the best shape after calculation, instead of the optimization within the hold or within this condition was fixed. So this is more freely to use for the conceptual designs. And so I'll try to explain what is the topologic for you. Topology just means the space and configuration and transformation of the object. We all know the alphabet from A, B, C, D, E to O, P, Q, R. And in the alphabet, indeed, the A and R, they are the same topology because they have one shielded areas. They all have one shielded areas and two bracing. That's the same. D to O, they are in the same topology because D has the shielded areas, O also one shielded areas. That's different from B because B have two shielded areas. And yes, actually from D to C, they are not in the same topology because C is open and D shielded one area. Of course, O and the job. O has one shielded area and job has no area inside. So this the topology. If the configuration of the object are the same, we could treat them as the same topology. If they are don't, we treat them to different topology. So topology optimization, that means we could change the configuration of the object freely to find the best shape to supporting the load. Such as in this case, we have two fixed points in here, and if we give two loads from the top of the middle, and step by step, and we could find out that the shape will be optimized like this, because in this situation, the load was transferred to the foundation directly. So this is supposed to be the best configuration for these cases. And today, the topology optimization was applied widely. We could find out that in the building, aircraft, motorcycles, bridge, and medical treatments, satellite antennas, bracket, and it's wide use. So today I will introduce one very simple and easy to use method to you that's called bezel. And now we will try to learn something about the theories of the bezel. Before talking about the theory of bezel, I will try to introduce the ESO for you. The evolutionary structural optimization method was proposed by Yimin Xie and Steven. And this optimization method was proposed just to improve the structural efficiency and shorten the design cycle. The inefficient materials in the structure are gradually removed to allow the structure to evaluate into an optimal forms. This is the example. if we give a hold inside a qubit areas and step by step, this is what remains, because this is for the load to hold, for the places to hold the structure, and the other will be delete according to the standard. I will explain the standard later, and step by step you could find out that this thing is more or less like the apple. So we could tell that the apple was shaped by the gravity and with engine. So here is the formula for the standard, how to or when to delete or where to delete the elements. I think this is quite simple, quite easy to understand. Firstly, A is the desired variable vector. This is all the vectors. The target is to minimize the weight, the total structural weight, to minimize the total structural weight. And we will delete the elements according to these criteria. Sigma E is the stress of the E element, and sigma mass, the maximum stress of the structure. So the RRI is the evolution rate and deletion rate, such as we give 0.2 to the RRI, and sigma E divide the sigma mass if they are less than 0.2, and all this material will be select and delete, so that the element with the high stress will be kept. This is the theories of ESO. It is very easy and very easy to be programmed, but there is a shortage for the ESO methods, and sometimes in the case like this, this is a 3 meters like the elements, and this is 4, and this is 30, and this is hinging elements. The fourth situation is 2 press to the left and 1 to the lower part of the structure. And after the optimization, because this 2 force to the left is dominate the structure, and the 1 is not so dominate, maybe the element will be optimized like this. This was remains because to resist this element is needed to resist the force, the load 2, and this element will be removed because this stress 1 is not so dominant, and the element was removed and they have no way to get them back. So the structural system may change, and actually without this cable, without this element, all the system was changed, and definitely not so good as that one with the hanger, with this hanger. So and the other situation is that the metric could be singularity, like in this case the stress surrounding here are less, and then we removed and some elements remain in the middle. Now the matrix will be singularity and the calculation will be stopped. And indeed this is not the very good solution. So how to treat with this shortage? And then the Yimin shared and Steven, they propose another method that's called bidirectional evolutionary structural optimization that we call BASO. We could see from the theory, from the formula, Formula 1 is the same with the ESO, but they give Formula 2, 3, and 4 to get the remove the element back. By this mechanism, they get the gamma. This is gamma. The gamma is the E divided to E time E to M powder. The EM powder may be the 10 to -4 -4 powders plus -4 powder multiply it. And if the sender is required, the gamma sigma E just larger than the RRI, then this material will be get them back, but not directly to the structural material. They give them a medium material called artificial unit. And if the other standard was meet like this, that means if they found them JR is the maximum stress unit density variance around the structure, usually 0.8 to 0.9. The sigma L is the number of the artificial unit. If artificial unit multiply JR still larger than the sigma means M, then this material will be set as the normal material and the rest one will be removed. So they give a mechanism for the removed unit to coming back. That's very that's a good idea, because delete or remove, they could get them back. Is the when to quit the cycle, we need to use the cycle again and again to select the useful units or useful element and keep them. And we need to invent a pipe. That's the sigma mass 0 V0. That's the very original initial domains. That's the first in the first circle. In first cycle, we have to mark them out, and then in every cycle, we need to find out that the sigma mass in the I circles, and at that time the V, that means the volumes at the I cycles. Then you made them sigma mass 0 V0 divided to sigma mass I and VI, and this is PI. And if PI drop during the cycle, and then you could quit, and that would be the best suitable solution. So that's the theories. And with the basalts, the efficiency was improved like this, and this element will not be deleted in the end. Instead, they will become very slender elements, and this one could be doing the optimization like this. Okay, that's slender, and this one will already keep. So this bezel is easy to use and easy to program. Then we need to talk something about the algorithm, how to program the bezel. I know the theory is easy. That's we find out the unit or element with the low stress, and then remove the unit or remove the elements, and step by step we have the final shape. Of course, with the bezel, we will tilt the element not so less stress with not so less stress, and we will try to get them back to the to go as the normal elements or normal stress. So this is the bezel algorithm with the formula from 1 to 5. And so when we try to make the programs of this algorithm, we need to firstly define two types of elements, one for optimal reason and one for unoptimal reasons, and two types of materials, one for normal elements and one for artificial elements. Parameter, we need at least 22. We have to get the mass and minute stress or sum of stress and so on, and element number and so on and so on. And array, we need 2 arrays to get the stress of every light or artificial elements, one for the live and one for the artificial. And then we have to calculate, we have to tell, is that meet the standard or not? If they meet the standard, we could get them back. If they don't meet the standard, we could delete this unit finally. And we also need the component, 5 components, define the collection for artificial units and the qubit units. The component is named group. We need to put all of the artificial units as a group so that we could select them easily in the next cycle. Or we put all qubit units into one component as one group so that we are easily to select them out in the next cycle to get them back. So this is the program. I use the APDL of ANSYS to make this program. Firstly, we could see that we divide 2 element type. We use plane 82, and we divide 2 materials. One is for the normal elements, and the other is for the artificial elements. And you can see they are the 10 to -4 times powders. And then we build a model from K, and then we use the divide them into the into finding elements like this. And here we have to remind you that is the large deformation effect we should keep it on, and the Newton-Raphson option we also should give them on, and nonlinearity we also need them on for the calculation. And after this, we need to ask something about the evolution rate, such as the 0.03, and also the define the terminal rates starting or terminal of the evolution from 0.03 to 0.2, and also ask the evolution step. This is the step, and also need to because in every step the element will be less and less, so we have to redefine the mesh to make them good. So this is the answer for this is the ask for the redefined mesh. And then in the right, we have to set the parameters to get the stress in every cycles, get the maximum stress, minute stress, the sum of the stress, and so on, and the amount of the light structural elements. And actually, this is something difficult. You can screen. You can press the screen down, and then you can after this webinar, you can try in the ANSYS or other program language. That would be the same. And then the amount of light structural elements and the artificial elements and so on. Number of delete, number of births, that means bring them back. And after setting this, we can find this parameter in the Scholar parameters, in the Scholar parameter items. And this is all the elements numbered, and ER and phase and so on. And then after this, we can try to get the element number first, get the mass number of the element to this parameter. That means how many units we totally divide into. In here, in this case, we divide 1,250 units altogether. And then we will create the components, 3 for the artificial and 2 for qubit. Then finish. And then we could we could give the Borden situation, like fixing here and give 2 force in the middle of the top surface, and then we solved. After the calculation, the first calculation is the very important one, is the post, that we have to get the stress, all of the stress to the table, and get the measurement, the sum of the stress. That means all of the units have the stress. We have to sum them out and give them to the TS. And then the amount of lie elements will be counted and given to the SCL. And then we have to find out all of the lie structural elements, the stress of the live structural elements, and give them to the result array. And this is get the stress to the result arrays. Then between these one arrays, we have to find out the maximum stress unit and the minimum stress unit within these results. We could use vscan funds, the function of vscan in the ANSYS, and in the other language. So we could use the same function to find the mass and the minutes for the next calculation. And then we select the type, and we select mat1, and then we will try to tell. This is the standard. R0 is that we get the revolution rate, and the ms is the stress, and we select this element with the low stress. This means less than the R0 multiply ms. All the stress less than this will be select and kill it. Kill this materials or kill this unit or. And this is the main shape after the first calculation. And we could see that this part with low stress was killed. But this just for the ESO, we just kill the element, but we have to get them back with the artificial elements. So now we have to do the artificial ones. Then we will select sometimes the artificial elements will go close to the structure. Okay, so firstly we have to select the QD element adjacent to the existing elements. We all know that each element have four faces, 1, 2, 3, 4. So that we set the phase 4. That's for 2D. If for 3D, we know that they have 6. So this phase should be changed to 6 in 3D situation. And 4, we have to find out that element adjacent to this one. 1, 2, 3, 4, 4 element adjacent to this one. And then we will select, if they have, we will select them now. 1, 2, 3, 4. And then if this 3 and 4 belong to the live elements, then we have to select them out and keep 1 and 2. This is the artificial elements. You see, this one we have nothing, yes. So these 2 are yes, 3 and 4 are yes. But 3 already the live elements, then we have to select them out. Here, we have to select these 3 out and keep the element 4 and becoming the artificial elements. And from a cycle, we have to tell one by one, and then we find all of the element adjacent to all of these elements, and then we select. Here is the we select the lie element, and then will be keep the element adjacent to the existing elements. So by this way, we can choose the artificial element out, and this is 4 is the artificial elements. by selecting all of the adjacent folds, and then we select the live elements. And then the remains should be the artificial ones. And then we will do the next calculation to tell if this large enough to be kit or not large enough. Then we will remove this element at that time. So this is the artificial element step that we have to define them out. And then if we need to keep, this is will MP change to material 2 and EA live them all. That means call them back to be the artificial element. And next route, we have to tell if this stress in this element becoming larger or less. Larger, we will give them back, and less, we will remove them at that time. So by these cycles, we could tell every stress of every unit, and then we delete them or get them back. So like this, step by step, the shape of this structure will be become the best suitable shape, will step by step getting out. It's worth to mention that you see in this step, indeed, this elements was isolated at that time, but nevertheless, because we could get the artificial material back, so it didn't become strange, so the calculation could carry out. And a very interesting phenomenon is that we could go like from the maximum number of elements and step by step find and delete. And actually, we could start from the minimum number of elements. And step by step, the artificial element will be added, and the necessary one will be turning back into the normal elements finally. And the low stress, that one with low stress will be removed. And then step by step, we could find out this from. And that's interesting is that from the two-way, from the maximum number of elements or from the minimum number of elements, the final answers is almost the same. They all transfer the load directly to the foundation. That's very interesting. So that within different situations, we could use different methods. One is delete step by step. The other is get them back step by step. And the MP ones, queue all the MP one first and get them back step by step. These two very interesting algorithms. And so by this method, I think you should know the theories of Basel, and you should know how to make the program of Basel. Now we could take a look to the engineer application. Here is the first case, is Hangrui Yidongting Bridge in China. This bridge is a suspension bridge with a main span of 1,480 meters. That's a long suspension bridge, and this bridge is located here. This is Yangtze River, Changjiang in China, and this is Dongting Lake in Hunan province. And it's worth to mention that beside the bridge side, they have this very famous traditional Chinese building called Yueyang Building. And in this building, we could find out that they are good in reference. Aesthetic effect is good. So how to use the Basel program to find the best suitable shape for this project? And we do, yes, of course, this in 3D. That means the face we should change to 6 and found 6 surface adjacent to the units and file them out with 3D. And firstly, we define no optimized area. This is for the saddle. You know that the suspension bridge, we have to put the saddle on the top of the towers. And then here is the bearing for the girder of the bridge. This could not be eliminated. And we have the loads. The vertical is a strong loads from the whole cables to the pylons to the towers, and then the wing load and to the saddle and then to the girder, and the girder to the bearings like this. This is the situation we have to give, the load situation we have to get. And then we could do the calculation step by step, and you can find out step by step the shade will be calculated like this. And the interesting thing is that when the cost bin in here was removed and the calculation was stopped, that means you could see that the PIs going up and up and up, and suddenly they fall, going down. That's because the connection between these two columns was removed, and then the stress will be not good, and the PI, so the PI drop and will be stopped. So the biggest situation will be like this. The PI at the most high point is the best suitable situation. Like this, okay, with the core spin, that would be the suitable one. And actually, during the designing process, we argued for the shape of the pylons. I myself I preferred with one connection pin, and the other sometimes someone's call 2 is okay, and the others call 3 is better. So we argue all the times until that we use special to find the shape. Then I say that one core spin is enough for this bridge, and then the argue will stop. Then we use one core spin, because in this situation the space is empty and clear and simple, and could do a best could make the aesthetic design to the best. So under this situation, yes, this is just structure. We have to step by step to design, to give the feature to the pylons, or and then it's easy to be told. We make investigation to the culture and to the building, and to the and something. And this is the fluted. You know the fluted, pan fluted with music with good music. It's going like up. The bamboos going like step by step up is interesting. And the building of the Yueyang building, just like 1, 2, 3, 4, that's interesting. So we decide to use the referent to design the referent to the pylons. Then we use 1, 2, 3 step, and then use the section from small and then large again, and then to these pylons. Use the circle to connecting the two columns up to this shape. But we need to give the Leiden load to the towers to prevent the lightings. So after the lightings was given, and here we made the decoration, and it lets the bridge look elegant. So for the best aesthetic effect, we also use the golden section. You know that the 0.61A. This is the golden section to arrange this part. This is the core spin lower part, and this is the first connecting point until the higher core spin. We use the golden section to arranging these elements, and then from this one to the top, we also use golden section to arrange these elements. And then, so you could find out that from this part is not easy to be solved by people. And so we start from here to the foundation. All this height of the pylons, we use golden section to arrange every details so that the bridge could be look elegant and beautiful. And this is the construction stage of the pylons, and this is the bridge construction finish. And this picture taken by Professor Eugene. He go visit this bridge a few years before. And the second cases I try to introduce to you is the Atlantic Bridge. I myself involved into the conceptual design of this bridge, and the aesthetic design. I also finished the aesthetic design of this bridge. This is the cable stayed bridge with a wingspan of 530 meters and crossing the Panama Canal. And this is the bridge site. It's located in the Colon City, connecting to the west part of this city. And this is the dock of the canal. And before we doing the vessel analysis, and the designing group just made the analysis for the seismic analysis, and they found that the lateral displacement of the pylon heads will be decreased with the lower part of the pylon dimension increase until this is 20 meters, and the lateral displacement will be less because the Panama is a country with strong earthquake. So we have to take the seismic action into account before we do the conceptual design. So this time we are just put this lower part like 60 meters. This is 60 meters wide to restrict the lateral displacement on the top. And then we remove all the unnecessary materials out and just keep the important ones. And then we give them loads, give the wind loads, and this is for the this is also the basic model for the transportation. This was kept for the transportation, but later we remove the useless element and then keep this one for the calculation. By this way, indeed, we could see that the during the optimization process, step by step, the unit was adding back, and then we move them again, and later finally to the shape of this, like this. From the process, we know that the PI becoming two P's. Firstly, to here, like this point, but not the high gaze. And this time the VR is going down and not to the end. So we tell that this one are not the terminals. And then to this one, they dropped dramatically. So this one would be terminal. And the PI is going up, but the VR going up and PI drop, they are inverse, so that we terminal the computer terminal the cycles, and this is the final shape. And so I mean, the bezel optimization, we could follow the best use of materials, but sometimes to the modern bridge, that is not enough for the aesthetics. So we still need to put some efforts to design these pylons. And that's very interesting is the dock. The dock of the canal is going like the V shape. So we use the V shape here and here to design the pylon according to the Bessel and the Bessel solution, the Bessel answer. But actually this lower part was just not so elegant, too strong. So we put a curve inside the columns, outside the columns to put a curve, and then with this curve, and the bridge could be look so slender, not so strong as the first one. And then we also use the V shape to the section. You see, this is also a V, so that the pylons could be look in light and shadow, so that it's more slender from the contrast of light and shadow. And then under the calculation, in the rule project, we find out that here the stress concentration is still a little bit high, so we have to fill these areas like this, and then we also use the Sequeir's proportion method to make a optimization for the shade of the pylons, and also use the golden section like this. This one is almost like the golden section to the white of the pylons. And yes, the deck, the height of the deck and the total height of the pylons, we also use golden section for the arrangement. So that from the very beginning, from the Bessel results to step by step, we made the optimization for the shade of this tower, and then we make it like this finally. And this bridge was constructed from maybe 1915 and 1913, and then this bridge was finished in 2019. And this is Antarctic Bridge, and this is the construction stage, and you can see that this is in light and shadow, and the pylon is look a little bit elegant with the curve and with the cut and with the light and shadow. And this bridge, this is the image taken after the bridge was constructed, and I think by this way we are finding a pylons or a towers good to resist the seismic force, and also have a biggest performance under the wind, under the vertical loads by the use of the Bessel. So, and I think this is my my lectures about the from Bessel algorithm to the practice of the engineering use. And I think thanks for all of you to listen this webinar, and thanks for all. And yes, we could start the question and answer now. Thank you, everyone. And before this, I just write my emails in here. If anyone interested in the structural optimization, you could send me the emails, and we could contact later. Now is the question and answer time. Firstly, I think Professor Eugene's topic is the first one. So now we will focus on the first one first, and then to the second topic. Okay.
Okay, let's come to the 3 questions related to my presentation. The first one is presentation slides. I make them available for everybody. I will send a PDF file to the webinar organizers, who can then upload them on some website. Second question, what are the advantages of UHPFRC? UHPFRC has all advantages that you can imagine. compared to other materials. This is the mindset you should have now. Afterwards, it's of course a question of design, a question of optimization and know-how, how to do it, how to work with this material. So you need to have a deep understanding of this material in order to find an optimized and technically efficient design. If you achieve this, the cost will be reasonable or even lower than what you would have as cost in traditional construction. Then the third question is about the application of UHPFRC in composite beams. As I mentioned and showed examples, it's a very effective method and material for composite designs, either with steel or with timber. The reason is UHPFRC is much better than a concrete slab. Concrete is a traditional material with rather moderate properties. If I put here concrete and I put here steel, then we have quite a big difference. If I have on this side UHPFRC, we are much closer. We have, let's say, almost equal partners. And this combination is much more interesting and technically efficient than when you have a big difference. That's why I would like to encourage you really to consider UHPFRC for composite construction particularly. Okay, that's all for the 3 questions in the Q&A box, but there might be more questions, please.
Any more questions? No? Okay, thanks for Eugene. And I also have a question for you about the timber. I think this very interesting, timber with UHPFRC. So is that the rigidity of this kind of bridge combines composite with timber and UHPFRC? We know that UHPFRC structure is something cylinder, and then we put the cylinder UHPFRC onto the flexible timbers, and how to make a balance between the rigidity and or cylinder or flexible or the strong of the structure.
You mean the connection between the 2 materials?
Yes, first is the connection. You know, it's easy to slip because UHPFRC is strong and timber is something flexible. This is the 2 different kind of material, and the flexible are totally, maybe we could say, different. Combine them together, how to firstly connect them together, and then how to consider the whole structure, the flexible of the whole structure, or the rigidity of the whole structure. Is that strong enough to take the load, especially for the heavy truck? Yes.
Yes, of course. The bridge I showed is actually used for trucks, heavy trucks that are transporting timber, large timber loads. And the connection, we simply use the connectors that are available for traditional timber concrete composite beams. And knowing that this is probably significantly over-designed, and in this way, the connection is, in this design, certainly not critical. The critical element or the critical part of the composite section is the timber intention.
Okay, thank you.
And In the analysis, we assume a stiff connection, like in traditional timber concrete designs. It would be interesting if we had the money to do some tests on it, load tests, and then compare the deflection with analytical predictions in order to calculate back the effective stiffness. But it must be very high.
Okay, I see another question for you in practical engineering. Yes, how to effectively combine UHPFRC with other materials to achieve complex structure while maintaining its performance advantage.
Wait, we are in the Q&A box now.
Yes, in the Q&A box.
I answered the first 3 questions, and then comes the anonymous attendee. Oh, wow.
The HS.
Oh, the last question is related
Yes.
to UHPFRC. If I may take that one, how to effectively communicate with other materials to achieve complex while maintaining the performance advantages. Yes, that's the ingenious of the engineer who needs to find out the answer to this question. You will not find the answer in a code or maybe in a good book or in a good article. That's why we are engineers, to know what are the properties, the performance of all the materials involved in such designs, not only UHPFRC, but also steel. Should we choose high strength steel or even higher strength steel, or is it okay to use just a lower strength steel to combine it with UHPFRC? This depends on the forces we have to take in such cross sections. So it's about knowing the structural performance of all materials involved, and then optimize, which usually means reduce the amount of the material to the strict minimum necessary. And there are, of course, numerical tools, analysis tools, optimization methods. There are books about it and so on. But in the end, it's up to the engineer to do that. And optimization has also to do, of course, I should have mentioned that, with the construction method. When you do a conceptual design of a new bridge, you have to think very quickly about how to build it. It depends very much on where the bridge is located, how it is accessible, and also what are the foundations. Yes, the soil conditions. A big advantage of lightweight structures is, of course, that the foundation is much cheaper when you have difficult soil conditions, when you use a lightweight structure. So this can also be a huge argument for UHPFRC construction. So I hope that this answers this UHPFRC question. And now, Xiaoyu, there are 2 questions for you.
Yes, here is a nominal audience have briefly introduced Basel algorithm. Indeed, the Basel algorithm is just to remove the useless materials or the material with low stress. We remove them off and keep the material with high stress. And that means sometimes the high stress material is necessary for the force to transfer inside the structure to the foundation. So that's, we remove the useless one and keep the necessary one to make the structure lighter. Just like our background image, you see that all of this, something like cheese, is going the necessary, and the other one is not so high with the stress. We could remove this material. That's the vessel, but we have to give the mechanism to let the delete material back, to get the delete material back. Sometimes in some circles, maybe and very important materials was delete. And in the very beginning, ESO programs, we could not get them back. But Bazel, we could use the artificial materials to get this coated material back, so that the system, finally we have the system reasonable, instead of focal into instead of get the low code optimized solution, instead of the very indeed the real best solution. That's Basil. We step by step remove the useless material, and sometimes the delete material we could get them back. That's Basil. Okay, thank you. And any question? Because we still have 2 minutes for the webinars, 1 minute for the webinar, and then in 4 minutes later, this screen will be shut. And again, thanks for Professor Eugene for your excellent lecture to give us new knowledge about UHPFRC.
Thanks for your invitation. Thanks the audience for attending it.
Yes.
It was my pleasure.
Okay, and thanks for the audience for the lecture of structural optimization on modern bridges, and also thanks Brindas and Ferret for the operation of these webinars and test of the webinars. Seems to have question. About the presentation, slabs of presentation. Maybe you can send me the emails. And I will ask the permission of Professor Eugene, and then I could send you. Just send me the email if you need the PPT. And Eugene, still one question for you. I think
I read the very last one. Using UHPFRC can reduce covering for durability. So the type of question betrays you. You are somebody who thinks in terms of reinforced concrete. Okay, so we do not compare directly the cover thickness for rebars, reinforced concrete, and cover thickness in UHPFRC. These are completely two different problems with completely two different solutions. In concrete, of course, we have to put a thick rebar cover, particularly when we have chloride ion attack. In UHPFRC, we have no requirement regarding durability. The cover is can be reduced to 10 millimeters. Why 10 millimeters? 10 millimeters is necessary from a mechanical viewpoint in order to transfer the force from the rebar to the UHPFRC or vice versa. That's the answer I would give here. Only mechanical.
Okay, thank you. Thanks again. So Brinda, everyone, if there are not any more questions, then thanks for all, and have a good day or good night or good afternoon, and see you next time.